Hello, in this one, let's take a trip down another mathematical black hole. So what do I mean by that? Take a look. Here's a relatively non-menacing looking limit. Limit as x approaches positive infinity of cosine sine inverse of x. So we're going to find this limit and then let's take a look. So for example, first, it's really helpful when you encounter one of these expressions that has like a cosine and a sine inside it to rewrite that x as, for example, like x over 1. You need that because based on that understanding, you can draw a picture of a triangle. Let me enable my grid here so I can make a good looking triangle. Okay, let's make a triangle. So for example, in this context, this could be our long side, the hypotenuse. This will be our adjacent, and then this will be our vertical. So based on the fact that it's a sine inverse of x over 1, the sine inverse function is the one that gives the angle. So in other words, what it's saying is that the angle, we'll call this theta here, is equal to sine inverse of x over 1. So that means if the angle is here, then this has to be x and this has to be 1, which means by the Pythagorean theorem that this has to be 1 minus x squared for the horizontal leg. So what I can do next is our limit says the limit as x approaches 0 of cosine of sine inverse of x over 1, but cosine is now cosine theta. Since sine inverse of x over 1 is theta, I can rewrite this limit equivalently as the limit as x approaches positive infinity of cosine theta, since theta is defined as you see there. But then, take a look. Look at my shape here. So for example, this side, that's the adjacent side, so I can simply take that and divide it by the 1 because that's the definition of the cosine. So if I do that, I will have the limit as x approaches positive infinity, and then cosine can be replaced with 1 minus x squared. Now in a previous video, I talked about this limit. So specifically, I showed that its value is I times positive infinity. So you're going infinitely far along the I-axis in a complex plane, whatever that means. Why is that the case? Just to remind you, so specifically imagine a simple situation. Imagine x is the value 10. Then if you plug that into this expression, you would have the square root of 1 minus 10 squared, which would be 1 minus 100, which would be the square root of negative 99, which, because there's a negative under the root, becomes the root of 99i. So it's a square root of 99. That's almost like the square root of 100, which is about 10, but perhaps a little bit less than 10. So it's say 9.5 or something like that I. And if you continue this process, you will see that the outputs from plugging in increasing values of x will always have an I in them. So again, just to emphasize this key point, it's basically as if we were doing this, just traveling straight up the I-axis in the complex plane. So let's say, call this 1i, this would be 0 here, that's I. Okay, say this is 2i, say this is 3i. I'm deliberately making these marks bigger so that the numbers don't overlap. Okay, so now then this one here would be 4i. Okay, say this one would be 5i. So I would be basically traveling up this axis in this direction, say from bottom to top, and then eventually up here I would be heading towards I times positive infinity, like that basically. So that would be the value of the limit for that reason right here. This. That's still, I think, somewhat understandable. But then here's perhaps something that might take us into a rabbit hole, so to speak, which is, imagine this triangle. It's just a triangle, and let's draw this triangle in a couple different cases so we can illustrate some things. For example, imagine that x has the value 1. If x has the value 1, then the hypotenuse is 1. Okay, let me grab this one. Okay, imagine this is the hypotenuse, but x also has the value 1, so that means that here would overlap this way, like that. So in this context, this is like saying that the blue is x equals 1, and then the brown over here, let me zoom in on this so we can separate things out. You gotta see, this would be that the hypotenuse has the value 1, and x equals 1. Then the question is, what is the bottom, the yellow part? Well, that's the square root of 1 minus x squared. So if you work that out here, it would be 1 minus 1 squared, which would be the square root of 1 minus 1, which is the square root of 0, which is 0. So that's still not a problem. But then, let's take this one step further than what we have here. Imagine that we do this instead. Assign a new value to x. So imagine that x has the value 2. So, the hypotenuse in our triangle is always equal to 1. X, which is the vertical leg, and then the square root of 1 minus x squared is the horizontal leg. So if we just assign x to be 2, say in this context, this is the hypotenuse, that's equal to 1 as before, so that's nothing new here. Hypotenuse is 1. But if that's the case, then since, as you can see here, this is x, and x has the value 2, then the vertical leg now has the value 2. So in other words, it would look like this. Imagine that it basically folds straight down this way. This would be now the vertical leg. Pretend kind of it's aligned with the hypotenuse, but the value of the vertical leg here is x equals 2. And then the question is, what is the horizontal leg? I'm not sure that we can picture that anymore, because if you work out its value, you're going to end up with the following. So I'm just going to put that over here, as if we were kind of pretending that it should be located somewhere over here. I would have 1 minus 2 squared, which would be 1 minus 4, which would be negative 3, which would be then root of 3i. So you have a triangle with a hypotenuse of 1. One of the legs is 2, which means the third leg disappears from our reality and reappears in the complex plane, and its value is the square root of 3i. Now I can mark that on the number line, but I can't actually visualize that. I've never seen the square root of 3i in this our particular reality. We have a way of charting it or depicting it on a graph, but that is not the same as being able to measure it. I've never seen a ruler that says, 1i, 2i, 3i, and 4i. What would that mean in this world? So it's kind of interesting that here, this third leg becomes a complex valued quantity and disappears, basically. So I've zoomed out here so you can see the whole process from top to bottom. Thanks so much for watching.